Have you ever just stopped and wondered what makes AI so ridiculously fast? I mean, how a huge language model can spit out an answer almost before you finished asking the question. Well, a lot of that secret sauce comes down to one tiny, almost magical line of code.
Right here. If you've ever dabbled in a deep learning framework like PyTorch, you've definitely seen this. It looks so simple, right? But typing .2 to CUDA is like casting a spell that connects your AI model to a supercomputer hiding inside your machine. It's the command that kicks your model off the regular processor and onto a high-performance GPU, making it unbelievably faster. But what is CUDA? What's really going on under the hood when we run this command? It honestly feels like magic, but it's actually this incredibly clever system of engineering that completely changed the game for AI. And that's exactly what we're going to unpack right now.
So at its core, CUDA is the language that lets us talk directly to the GPU. Think of it as the bridge between that simple Python code we all write and the thousands of specialized cores sitting on that graphics card. It's the instruction manual that tells the GPU exactly how to handle the massive, heavy-duty calculations that AI needs.
Now, to really get this, you have to understand that your computer basically has two different kinds of brains working together. In the CUDA lingo, we call them the host, that's your CPU, and the device, that's the GPU. And you know what? They are built for completely different kinds of jobs.
Here's probably the best analogy for it. A CPU is like a Formula One car. It is all about low latency, meaning it can finish one complex task incredibly fast. A GPU, on the other hand, well, that's like a massive cargo ship. It's all about throughput. It's slower to get going, sure, but it can move an absolutely enormous amount of cargo, or in our case, data, all at the same time. And you can literally see why when you look at their architecture. The CPU on the left, it dedicates all its space to just a few super powerful cores with big caches. It's a specialist, a genius at doing one thing at a time. The GPU on the right takes the exact opposite approach. It's jam-packed with thousands of simpler cores. It's not a specialist. It's an army, ready for massive parallel jobs.
So the crucial thing to remember is that these two brains have to talk to each other. Every single CUDA program follows this fundamental four-step dance. The CPU, our host, acts as the project manager. First, it sets aside some memory on the GPU. Second, it copies the data over. Third, it tells the GPU, okay, go run this job. And finally, it copies the results back. This flow is everything.
So, how does our CPU project manager actually give instructions to the thousands of workers on the GPU's factory floor? Well, it does it using two really important concepts: kernels and threads.
A CUDA kernel is really just a fancy name for a special function you write that's meant to run on the GPU. But here's the twist. Unlike a normal function that just runs once, a kernel is designed to be launched in thousands of identical copies, all at the exact same time. And this right here, this is the most powerful idea in all of CUDA. You don't write code for 1,000 different workers. No way. You just write the instructions for one single worker, which we call a thread. You define one small, simple task. Then you tell CUDA to launch thousands or even millions of them, and the hardware just handles running them all in parallel. It's brilliant. So yeah, each of these threads is like one individual worker on that massive factory floor. If you have a million numbers you need to add together, you don't write a loop that goes one by one. Nope. You launch a million threads, and each thread performs just one single addition. That is the very essence of how GPU computing works.
Okay, so we've got this amazing parallel processing machine. But why is it such a perfect fit for AI? Why did GPUs suddenly become the engine that powered this whole AI revolution? Well, the answer is in the math of deep learning itself.
It turns out that pretty much every core operation inside a neural network is what computer scientists call embarrassingly parallel. Things like activation functions, those huge matrix multiplications, updating gradients, even the attention mechanisms in transformers. They all follow the exact same pattern. You are doing the same simple operation on millions of different pieces of data at the same time.
Let's make this super concrete. Take an activation function like ReLU. All it does is look at a number, and if that number is negative, it turns it into 0. That's it. So if you have a matrix with millions of numbers, you can assign one thread to each and every number. Every thread does that one simple check, and poof, the entire operation is done all at once, almost instantly.
And that right there, that is the big aha moment. GPUs aren't just a faster version of a CPU. Their entire architecture, built from the ground up with thousands of simple cores, is perfectly,
fundamentally suited to the exact type of math that powers modern AI. It's a match made in silicon heaven. But hold on, because just getting your code to run on a GPU is really just step one. The real art, and where the incredible gains are made, is in optimization, making it run as fast as humanly, or I guess as fast as siliconically possible.
You see, a basic, naive CUDA program can actually be slower than a function in a highly optimized library. The engineers who build these systems, they spend their entire careers figuring out how to squeeze every last drop of performance out of the hardware.
This optimization ladder gives you a pretty good idea of that journey. You start at the bottom with a simple version. Then you start climbing. You optimize how data moves around in memory. You start using specialized parts of the chip called tensor cores. You use advanced algorithms like flash attention. Each step builds on the last, and the speedups just keep compounding. And the performance gains we're talking about are just staggering. Just by optimizing your memory access, you can get a 7x speedup. A fully optimized kernel, like the ones used in real-world AI, can be over 20 times faster than that first version. I mean, that's not a small improvement. That is absolutely transformative.
So why does this all matter? Well, because a 20x speedup translates directly into millions of dollars in saved training costs. It means way less energy consumption, and maybe most importantly, it's what allows us to build the next generation of bigger, more powerful AI models that would just be computationally impossible otherwise.
Which brings us to our final thought. We've gone all the way from a single line of code to the absolute frontier of hardware optimization. And as engineers keep climbing that ladder, finding even more clever ways to make AI faster, it leaves us with a really fascinating question. What new capabilities, what new forms of intelligence will become possible next?